Hello everyone, welcome to my YouTube channel. So today I am going to discuss the linear algebra problems of CSIR NET 2023 June examination. Okay, so let's start. The first question says that consider the quadratic form QXYZ associated to the matrix. This is a 3 cross 3 symmetric matrix, and define a set S, that is collection of all vectors from R3 such that QABC equals to 0. The question asks that which of the following statements is false. So it's a very simple problem. You have to just compute the value of Q on ABC. That's just suppose B is here 3 cross 3 symmetric matrix. So QABC is basically this. So after computing, you will get A plus B minus root 2C into A plus B plus root 2C. Now it is given that if ABC belongs to the set S, that means QABC equals to 0. That means A plus B minus root 2C equals to 0, or A plus B plus root 2C equals to 0. So both are the equation of plane in R3, right? So S is union of two planes. That is true. Now on XZ plane, Y coordinate is definitely 0. Now in the vector ABC, Y coordinate is basically B. So B is equal to 0. So if B is equal to 0, that means A equal to root 2C and A equal to minus root 2C. That is two straight line. So AS is basically union of two straight line, but it is given that AS is an ellipse. Intersection of AS with XZ plane is an ellipse, but here intersection of AS with XZ plane is union of two lines. So second statement is false. Now first one statement is definitely true because intersection of AS with XY plane, that means Z coordinate equal to 0. That means C equal to 0. So if C equal to 0, A plus B equal to 0. That means A equal to minus B. That means X equal to minus Y. And this is a straight line. So option 1 is definitely true. And Q is degenerate quadratic form. This is also true because the associated matrix B is singular matrix. You can easily see that the first row and the second row both are same. That means it is singular matrix. So Q is definitely a degenerate quadratic form. So it's a very simple problem, and option 2 is the only false statement here. So 2 is the correct answer here. Okay, it's a very simple problem. So come to the next one. Given that A is a 3 cross 3 matrix whose characteristic polynomial Pt is divisible by t square, it is asked that which of the following statements is true. It's an MCQ problem. Okay, so A is a 3 cross 3 matrix. So then definitely the degree of characteristic polynomial is 3. Now t square divides pt. That means pt equal to t square into t minus lambda. Now take a matrix T where T is just like this: 0, 1, 0, 0, 0, 0 and 0, 0 lambda. So observe that the characteristic polynomial Pt also satisfies this matrix, right? So for this matrix, characteristic polynomial is T square into T minus lambda, because all the eigenvalues are this is an upper triangular matrix and all the eigenvalues are diagonal entries. Okay. Now dimension of eigenspace for eigenvalue 0 of this matrix T is 1, but algebraic multiplicity of T 0 is 2 here, but the geometric multiplicity for 0 is 1, so T is non-diagonalizable. Also T cube not equal to 0, because if T cube equal to 0, then this is an annihilating polynomial and this is a nilpotent matrix. This will imply that T is a nilpotent matrix, so all the eigenvalues must be 0. I should mention that lambda not equal to 1 here I considered to be lambda not equal to 0 here. I am considering lambda not equal to 0 here, I should mention there, but it's okay. So if for the non-zero case of lambda, it is definitely T cube not equal to 0. So only option 2 is correct, because we know that if a polynomial of degree 3 has at least 2 real roots, then it must have all the roots are real, because the complex roots occurs in conjugate form. I mean, if a plus ib is a root, then a minus ib is also a root of this real polynomial. So since it is already given that t square divides pt, that means it's all the roots of pt are real. So second statement is true. It is a very simple problem. Now come to the third one. Let A be a 3 cross 3 matrix with real entries. Which of the following assertion is false? This is also an MCQ problem. So similarly, a degree of characteristic polynomial is 3. Now if t determinant of t equal to 0, then t is non-invertible. That's when nullity t is not equal to 0. So nullity t not equal to 0, that means both A and B are true statement, because these are 3 cross 3 real entries. So since odd degree polynomial, that means it must have a real eigenvalue. I mean, odd degree polynomial must always have a real root. So A must have a real eigenvalue. So option 1 is correct here. Also, we already see the nullity t not equal to 0. That means 0 is definitely an eigenvalue of A. So option 1 and 2 are correct. Now, say A has complex eigenvalues. It is given that 3 is already an eigenvalue, right? So other eigenvalues, say A plus IB, then since it is comes in conjugate form, so A minus IB is also an eigenvalue. Now we know that determinant is product of eigenvalues, right? So here the product of eigenvalues is 3 into A square plus B square. So this is always greater than 0. I mean greater equal to 0, because I just greater equal to 0. So in particular, I can assume A in this form, right? 0, 1, 0, minus 1, 0, 0, 0, 0, 3. So here eigenvalues are 3, minus I and I. Then product of eigenvalues is 3, which is greater than 0, but all the eigenvalues are not real. So correct option is 4. So 3 is this correct statement, but since it is asked about the false statement, so option 4 is the false statement. So here the correct answer is option 4. Now come to the next problem. It is a very simple problem, but it's a tricky problem. Let L greater or equal to 1 be a positive integer. What is the dimension of the real vector space of all the polynomials in 2 variable over R, having a total degree at most L? Now, any polynomial of 2 variable is of the form, any polynomial of 2 variable of total degree n is of the form fxy, that is 0 less equal to I, j less equal to n, I plus j equal to n, aij x to the power I, y to the power j, right? So total degree at most L, that means a I plus j equal to L. Okay. So suppose I just considering the polynomial whose total degree is equal to L. That means I varies from 0 to L, and if I is k, then j is basically L minus k. So I have L plus 1 choice for I, right? And after choosing I, j becomes fixed, so we need not to count the choice for j. So I have L plus 1 choice. So total combination is L plus 1. So when degree is L, I have total choice L plus 1. So similarly, when degree is L minus 1, I mean I plus j is L minus 1, I have total combination L. So similarly, when I plus j is k, I have total combination k plus 1. So starting from 0 to L, now total degree is at most L, it is given, right? So total degree can be 0, 1, 2, 3 up to L. So for 0 I have combination 1. For total degree 1 I have total combination 2. For total degree 2 I have total combination 3. So in this way I have total combination 1 plus 2 plus 3 plus dot dot plus L plus 1. So which is equals to L plus 1 into L plus 2 by 2. It is very simple problem. If you have doubt, just write down a polynomial in your way and just count it. So it is obvious. So option 4 is correct answer. Now come to the next problem. X is a n vector in Rn and y is also a vector in Rn. So here it is asked that which of the following defines an inner product on Rn. So we already know the definition of inner product, and we also see whether it satisfies the condition or not. Okay. So suppose I take n equal to 2. It becomes easy. So suppose take n equal to 2 and choose x equal to 1 comma minus 1. Then for first part, inner product x comma x is basically 1 into 1 plus 1 into minus 1 plus minus 1 into 1 plus minus 1 into 1, which is 2 minus 2 equal to 0. We know that inner product x comma x is always greater equal to 0, and inner product x comma x equal to 0 if and only if x is equal to 0. But here x not equal to 0, but x comma x, I mean inner product of x comma x is basically 0. So that's why this is not a inner product. Okay, so this is wrong. First statement is wrong. Now for the second statement, inner product xy is defined as summation xi square plus y square. So inner product cx comma y is summation c square xi square plus y square, which is not equal to c into xy, because if I do c into xy, it becomes c xi square in plus c y square, but here it is just yi square. So I just take c not equal to 1, because if c equal to 1, then nothing to prove. So for c not equal to 1, it does not hold. So that's why this is also false. Now similarly for the third one, I can again take n equal to 2 and x equal to 1 to 0. That means inner product xx, that means inner product 1 0 comma 1 0, which is 1 into 0 plus 0 into 1, that is also 0, but x not equal to 0. So 1 2 4 all are wrong here, so only third one is correct. Now third one is very easy, because we know the standard inner product on Rn is basically summation j equal to 1 to n xj plus xj into yj, right? So here it is just a product with j cube, so it will definitely satisfy all the condition. If you check the condition, you will definitely see that it will satisfy all the conditions. So third one is correct. Now come to the fourth question. I'm sorry, fourth or fifth, I know. Okay, so come to the next question. So let T be a linear operator. I think it is fifth question. T be a linear operator on R3, and fx belongs to Rx in the characteristic polynomial. Suppose T is non-zero and 0 is an eigenvalue, then fx equal to x gx in Rx, then linear operator gt equal to 0, and also the next statement says that this is 0. So come to the solution. Let fx equal to x cube. I can take, right, because it is just given that t is non-zero and 0 is an eigenvalue of t. So I can consider the nilpotent operator on R3. So characteristic polynomial is x cube, fx equal to x cube, then definitely 0 is an eigenvalue. Now write down fx equal to x into gx, that means gx equal to x square, right? Gx equal to x square. So now if I consider t like this 0 1 0 0 0 1 0 0 0, then gt equal to t square not equal to 0. So a is definitely a false statement, because here t cube, minimal polynomial for t is t cube, so gt equal to t square is non-zero, so a is definitely a false statement. Now come to the second one. 0 is an eigenvalue of t with at least two linearly independent eigenvectors. That means geometric multiplicity for 0 is greater or equal to 2, right? We know that algebraic multiplicity always greater or equal to geometric multiplicity. So algebraic multiplicity greater or equal to geometric multiplicity greater or equal to 2. So algebraic multiplicity is 2 or 3. If algebraic multiplicity 3, then fx equal to x cube. Since geometric multiplicity 2 or 3, then minimal polynomial must be x or x square. So that will imply gt equal to t square is always 0. Because if minimal polynomial is t, that means t equal to 0. And if minimal polynomial is t square, then t square equal to 0. Since gt is equal to t square, so it will always 0. Now if algebraic multiplicity is t, then fx can be written as x square into x minus lambda, where lambda is the non-zero eigenvalue. Now am equal to gm, because for algebraic multiplicity of lambda is 1, so geometric multiplicity of lambda is definitely 1, and it is given that algebraic multiplicity of 0 is 2 and geometric multiplicity is greater or equal to 2. That means geometric multiplicity and algebraic multiplicity for 0 same. So in this case t is diagonalizable, because for both eigenvalue algebraic multiplicity and geometric multiplicity are same. So minimal polynomial, since it is diagonalizable, minimal polynomial is product of distinct linear factors. So minimal polynomial is x into x minus lambda, which is same as gx. So gt is definitely 0. So B statement is true. So here A is false and B is true. A is false, B is true. So option 4 is correct. Now come to the next one. This is a very simple problem. Very simple problem. Suppose A is a 5 cross 5 block diagonal real matrix with diagonal blocks. There is a 2 cross 2 block and here is a 3 cross 3 block. So first write down the matrix A. This is like this. Now this is a upper triangular matrix. So all the eigenvalues are diagonal entries. So definitely algebraic multiplicity of E equal to 5. Now we have to compute the geometric multiplicity for the eigenvalue E. So A minus EI is basically this. Rank is 2. So dimension of the null space is 3. Dimension of the null space is 3, not equal to 5. Hence 1, 2, 3 are correct options because algebraic multiplicity E is 5. A is non-diagonalizable because algebraic multiplicity 5, geometric multiplicity 3. And geometric multiplicity of E in A is 3. This is correct, but last one is not correct. So 1, 2, 3 are correct options. And also you can easily see because we know that there is a theorem. You can remember that geometric multiplicity of eigenvalue is number of distinct Jordan blocks corresponding to the eigenvalue. Okay. So actually here A is in Jordan canonical form. And if you can observe that, you can see that here it is 2 cross 2 Jordan blocks and 1 cross 1 Jordan blocks. So there is 3 distinct Jordan blocks. So that's why geometric multiplicity is 3. And algebraic multiplicity is 5, which is obvious from the upper triangular matrix. So its diagonal entries are eigenvalues. So we are done. Now come to the next one. This is a very interesting problem and nice problem. Let V is a finite dimensional real vector space and T1, T2 be nilpotent operator on V. W1 is basically the null space of T1 and W2 is basically null space of T2. So which of the following statements are false? It is asked. It is a MSQ problem. So if T1 and T2 are similar, then W1 and W2 are isomorphic vector spaces. And all the other options are if W1 and W2 are isomorphic vector space, then T1 and T2 have same minimal polynomial. And also in the next case, if W1 equal to W2 equal to V, then T1 and T2 similar. And if W1 and W2 are isomorphic, then T1 and T2 have same characteristic polynomial. These are the options. So come to the solution. If T1 and T2 are similar, that means rank of T1 and rank of T2 are same. That means nullity of T1 and nullity of T2 is same. That means dimension of W1 and dimension of W2 is same. Now we know that V is a finite dimensional vector space and W1 and W2 both are the subspace of V. So W1 and W2 both are finite dimensional, and it is enough to have same dimension to be isomorphic because if dimension of W1 is K and dimension of W2 is also K, then I have K many vectors in the basis and also I have K many vectors of W2 in its basis. So I just map first one to the first one of the I just map the first one vector of the basis of W1 to the first one vector of the basis of W2, second one vector of the basis of W1 to the second one vector of the basis of W2, and in this way I can just map K many vectors to K many vectors, and this will gives me an isomorphism. So definitely W1 and W2 are isomorphic. So the first statement is true statement. Now for this, now consider V is R4. Okay, so dimension of V is definitely 4, and T be the matrix in this way. T2 is also a matrix in this way. So this is an upper triangular matrix, and all the eigenvalues are 0. So both are nilpotent operators. So it satisfies our given condition. Now minimal polynomial of T1 is basically x square. You can easily observe, and minimal polynomial for T2 is x cube. So these one is false. W1 and W2 are isomorphic vector spaces. Then T1 and T2 have same minimal polynomial. This is false. Here you can easily see that both W1 and W2 have dimension 2, because here rank is 2, here also rank is 2. So here nullity is 2, here nullity is 2. That means dimension of W1 and dimension of W2 is same. That is 2. So they are isomorphic, but minimal polynomial is different. So again, in the third option, it is given that if W1 and W2 is equal to V, then T1 and T2 similar, which is obvious, because W1 and W2 equal to V, that means T1 and T2 are zero operators. I mean T1 and T2 are zero, so they are definitely similar. And if W1 and W2 are isomorphic, then T1 and T2 have same characteristic polynomial, which is also true. Even if W1 and W2 are not isomorphic, then also T1 and T2 have same characteristic polynomial, because dimension of V is n and T1 and T2 are nilpotent operators, then definitely the characteristic polynomial is x to the power n. Even if W1 and W2 are not isomorphic, this is true statement. So only false statement is second one. Though it is a MSQ problem, but also only one statement is false here. So correct answer is 2 just. Okay, is a very interesting and nice problem. Yeah, now come to this question. Many students have doubt in this question, so I think the answer should be challenged in this question. So T is R3 to R3 is a linear transformation satisfies T cube minus 3T square equal to minus 2i, and then the options are these. So just observe that T cube minus 3T square plus 2i equal to 0, and from here I can conclude that T has distinct eigenvalues. So since T has distinct eigenvalues, then T is diagonalizable. So since T is diagonalizable, then with respect to some basis, T is the diagonal matrix with diagonal entries the eigenvalues, and we know that any diagonal matrix is symmetric, and also it is upper triangular. So both 1 and 2 are correct. Okay, now consider the third one. R3 must contain a non-zero vector V such that TV equal to V. That implies that 1 is definitely a eigenvalue for T. But here T cube minus 3T square plus 2i equal to 0 is just an annihilating polynomial. And minimal polynomial just divides it. So in particular, if I choose T as 1 plus root 3 into I, this matrix, then this also satisfies the condition. I mean, for this matrix, T cube minus 3T square plus 2i is also an annihilating polynomial, but 1 is not an eigenvalue in this case. So 3 and 4 are false option. I think in answer key 3 also included as a correct answer, but only correct answer should be 1 and 2. Now come to the next one. It is a very simple problem, and we know that, and also I want to say that in Tp equal to P prime, I mean the derivative of P, this is a very important linear map and it occurs in many exams. Okay, so it is given that V is a real vector space of real polynomials in one variable with degree less than or equal to 10, including 0 polynomial, and linear map is defined as T of P equal to P prime. Now which of the following statements are correct? This is also a MSQ problem. So dimension of V is 11, so we just take the standard basis vectors, which is 1 x squared up to x to the power 10. Now our work is almost done, because we have to just find out the matrix representation with respect to these basis vectors B. I mean I have to find out the matrix representation of T with respect to standard basis vector B. Okay, so T1 is 0 because derivative of 1 is 0, Tx is 1, Tx square is 2x, Tx cube is 3x square, so on, and Tx to the power 10 is 10x to the power 9. So T1 is 0, so first column I just write down is as a linear combination of these vectors, and I just write down is as a column of first column vector. It's very simple. So if you find out the matrix representation of T, which is basically this, so you can observe that all the diagonal entries of this matrix representation of T is 0, and T is upper triangular matrix. That means the eigenvalues for T are diagonal entries. So all the eigenvalues of T are 0. So all the eigenvalues of t are 0. So fourth one is correct. Now we know that trace is sum of eigenvalues. So since all the eigenvalues are 0, that means trace is also 0. So third one is also correct. Now we know that determinant of t is product of eigenvalues. Now all the eigenvalues are 0, so determinant t is equal to 0. Now rank of t equal to 10. Here you can easily observe rank of t is equal to 10. Only last row is 0 row, completely 0 row. So rank of t is 10. So it is obvious. So 1, 2, 3, 4. All the 4 options are correct here. It's the MSQ problem. All the 4 options are correct here. So it's a simple problem, but nice. I'll come to the next one. This is also a very interesting and very important problem. So let V be a vector space of all polynomials in one variable of degree at most 10 with real coefficients, and W1 be the subspace of V consisting of polynomials of degree at most 5, and W be the subspace consisting all polynomials such that the sum of their coefficients is 0, and then given that W is the smallest subspace of V containing both W1 and W2, then which of the following statements are true? So come first. So it is given that W1 is contained in W and W2 is also contained in W, right? So dimension of W is greater than dimension of W2. Now what is the dimension of W2? W2 says that W2 is said to be that W2 is a subspace consisting of all polynomials such that the sum of their coefficients is 0. So only there is only one restriction, and which is on the coefficient. I mean, suppose the coefficients are a0, a1 up to a10, then sum of the coefficients are 0. That means a0 plus a1 plus a2 plus dot 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 a10 equals to 0. So I can write down a0 as a combination of other 10 vectors. I mean, a0 is basically minus of a1 plus a2 plus a3 dot 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 a10. So I can replace a0 by minus of a1 plus a2 plus dot 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 a10. Okay, so what is the dimension? Dimension is 10 because I have choice for, I can choose any real number for a1, a2 up to a10, and a0 is depends on these 10 choices, right? So only one restriction here, so dimension is definitely 10. So dimension of W2 is 10. Now dimension of W is greater or equal to dimension of W2, so dimension of W is greater or equal to 10. Now consider fx equal to x. This belongs to W1. Why? Because W1 is subspace consisting all polynomials of degree at most 5. So it is a 1 degree polynomial, I mean linear polynomial, so definitely it is inside W1. But this is not inside W2, because W2 says that sum of all the coefficients must be 0, but here sum of all the coefficients is 1, right? So fx equal to x does not belong to W2. Since W is the smallest subspace containing W1 and W2, so then definitely W not equal to W2. Okay, because W must contain W1 also, so W cannot be W2, because this fx equal to x must be inside W, but fx equal to x is not inside W2, so W2 is a proper subspace of W. Now dimension of W2 is 10, and it is a proper subspace of W, and also W is inside V, so dimension of V is 11. I have, right? Dimension of V is 11. So dimension of W is 11 equal to dimension of V. So W is definitely equal to V. So W is definitely equal to V. So dimension of W is at most 10. This is false because dimension of W is 11. So first one is wrong option. Second one is correct. And W1 is inside W2. That is also false because I have already fx equal to x, which is inside W1 but which is not inside W2. So third one is also false. Now what about fourth one? It is given the dimension of W1 intersection W2 is at most 5. So I have dimension of W1 is 6. Dimension of W2 is 10. Then dimension of W1 is intersection W2 is subspace of W1 and W2 both. So dimension of W1 intersection W2 definitely less equal to 6. Now if dimension of W1 intersection W2 equal to 6, that means W1 intersection W2 is basically W1. That will imply W1 is inside W2, but which is wrong, because we already see that fx equal to x in W1, but it is not in W2. So dimension of W1 intersection W2 cannot be 6, so which is less equal to 5, so it is at most 5. So correct answers are 2 and 4. It is a very interesting problem. I think is one of the good problems of linear algebra which comes in this, in this question. Okay. Consider the following quadratic forms over R. Here it is 6x square minus 13xy plus 6y square, and b is x square minus xy plus 2y square, and c is x square minus xy minus 2y square. Okay, so this asks that quadratic forms A and B are equivalent, quadratic forms A and C are equivalent, quadratic forms B is positive definite, and quadratic form C is positive definite. Okay, so these all are asked. Okay, so I just take let quadratic form QXY is basically XY, and here is the symmetric matrix A B B C, and also the vector XY. Then what about Q10? Q10 is basically gives me A, and Q01 is basically gives me C, and Q11 basically gives me A plus C plus 2B. Okay, I just write down. You also don't do it. It's no problem. So Q1 is, so for first one, if I consider 6x square minus 13xy plus 6y square is the first quadratic form, say Q1. Then for Q1 of 10 is 6, Q1 of 01 is 6, and Q1 of 1, 1 is minus 1. So the matrix associated with Q1, the symmetric matrix associated with Q1 is basically 2 cross 2 symmetric matrix with entry 6 minus 13 by 2 minus 13 by 2 6. And similarly for the second one, it is x square minus xy plus 2y square. So the quadratic form associated to Q2 is basically 1 minus up 2, and the quadratic form is associated to Q3 is basically 1 minus up minus 2. Okay, so the eigenvalues of the matrix associated to Q1 is basically 6 plus 13 by 2, 6 minus 13 by 2. The eigenvalues associated to the matrix of the quadratic form Q2 is basically 3 plus root 2 by 2, 3 minus root 2 by 2. And the eigenvalues associated to the matrix Q3 is minus 1 plus root 10 by 2 and minus 1 minus root 10 by 2. Now we know that both the quadratic forms are equivalent if both the quadratic forms are equivalent if their rank are same. If the associated matrix, associated symmetric matrix has same rank and same number of positive and same number of negative eigenvalues. Now just observe here that it is asked that quadratic form B is positive definite. So if a quadratic form is positive definite, that means the eigenvalue with the associated symmetric matrix definitely positive. Now for B, both the eigenvalues are positive, but for C, these eigenvalue is negative, these eigenvalue positive. So C is not positive definite, but B is positive definite. So here option 3 correct, but option 4 false. Now for quadratic form A, I have the associated matrix has one positive eigenvalue, one negative eigenvalue. Here both two are positive. So number of positive eigenvalues are different for this one and this one. So A and B are not equivalent. A and B are not equivalent, but A and C are equivalent because here rank both the quadratic form, both associated matrices rank same, both have rank 2. This one is 2, this one is 2, and here it has one Negative eigenvalue, here it is also one negative eigenvalue, one positive eigenvalue, one positive eigenvalue. So all of these are same. I mean, there is a term which is called signature. Signature means number of positive eigenvalues minus number of negative eigenvalues, which is also same as here. So that's why 2 and 3 are correct answers. Okay. Let B be a 3 cross 5 matrix with entries from Q. Assume that V belongs to R5 such that BV equal to 0 is a three-dimensional real vector space. So which of the following are true? So which of the following are true? Here B is a 3 cross 5 matrix from entries from Q, right? So I can think B as a linear map from R5 to R3, which I have named TB. That is basically a linear map from R5 to R3. So dimension of V belongs to R5 such that BV equal to 0 is 3. It is given. Then dimension of kernel TB is 3 because this is a linear map, so kernel TB is 3. These vectors are in the kernel of B, so kernel TB is 3. Then dimension of range of TB is basically 5 minus 3 equal to 2 from the rank nullity theorem. So rank of B is 2. Okay, so because dimension of range of TB is 2, which is same as rank of B, so rank of B equal to 2. Now now this has 3 dimension over R, and Q is the subspace of R, right? So sorry, so Q is the subfield of R, right? So if it has dimension over the field, then field R is 3. That means the dimension over the subfield also 3, because if the dimension choose 3 vectors which are linearly independent when we are considering it over R, say v1, v2, v3. So these are the basis vector for this space. So if dimension is less than 3 over Q, that means I have a non-zero linear combination, say q1 v1 plus q2 v2 plus q3 v3. q3 v3 is equal to 0, where qi belongs to Q, but Q is also inside R, right? So if there is a non-zero combination which gives us the 0 vector, then this will imply this non-zero combination works for real entries, real field also, right? So these 3 vectors becomes linearly dependent on real field over real field also, which is a contradiction. So since it has dimension over R3, then it has dimension over Q is also 3. Now given that the linear map T B is equal to B transpose B is injective, and B transpose B is injective, so the map is Q3 to Q5, it is injective. That means the kernel T has dimension 0, so range T has dimension 3 by rank nullity theorem. So rank of T is 3. Then rank of B transpose is basically 3, because this linear map is actually the matrix representation of the matrix. This linear maps representation, matrix representation is basically B transpose. So the rank of B transpose is 3. But we already observed the rank of B is 2. Then definitely rank of B transpose is also 2, but it gives 3, so these are wrong. Now rank of B is 2. That means column span is 2-dimensional. We know that the column space, dimension of the column space is same as rank of the matrix, so the column span is 2-dimensional. So this is also a correct option. Now T is given that Q3 to Q3 such that T of V is basically B transpose B. So this is injective, right? So this is injective. That will imply that rank of T is 3 by similarly by rank nullity theorem, because injective means dimension of car T is 0, so nullity T is 0, so rank of T is 3. So this is the matrix representation of the matrix representation for T is basically B transpose. So rank of B transpose is 3. Now we know that rank of B transpose is less than equal to minimum of rank. Here is mistake, rank B and rank B transpose. Now rank B is 2, rank B transpose is 2, so rank B transpose is less equal to 2. That's a contradiction. So this is also a false statement. So only correct statements here is 1 and 3. So only correct statements are there 1 and 3. So I just discuss all the problems here. If you have any kind of doubt, you can comment below so that I can reply you. Thank you and keep watching. Please subscribe my channel. Okay, so goodbye.